Hello, everyone. All right. So, what I wanted to do is go back over a little bit of power and energy, and then complete chapter 8 with um, electrical concepts. I know I'm a little late on getting this video out, but I think it'll be helpful in trying to answer some of the questions when it comes to the exam. All right. So, one thing to keep in mind is for energy, um, some of your typical units is a BTU and a calorie, the CAL stands for calorie. And 1 joule is equal to 0.239 calories. And 1 joule is also equal to 9.48 times 10 to the minus 4 BTUs. BTU is usually the British international units, just like you have, system international units and American standard, American or United States. What is it? US, I think it's United States American Engineering, AS, or maybe American Standard Engineering Units. I can't remember. Sorry, guys. Trying to remember this right on the top of my head. But anyway, so ASE as opposed to British International and SI. So British International typically use BTUs for energy. Right. And so that's what a BTU is. It's also, I think we use it too, an American standard. I believe we use BTUs. But the conversion this is the conversion factor that you can see on my screen. Now, I'm not going to work a problem for energy, but what I do want to do is go to this problem in power. I saw a problem for power. And it's a pretty good question, I believe, because it asks you, we wish to provide 2,000 calories of energy in 30 minutes, right? And it asks you to determine the amount of power required in units of watts. So if you recall, a watt is a joule per second, right? Just shows you that. And we also remember 1 joule is equal to 0.289 calories. Oh, is that 289? See, I'm trying to do that from memory. 0.239. Equal to 0.239 calories. So we know power is energy over time. What was that equation? Energy over time. And so what you would do for this particular problem is you would divide. Well, first you would convert calories to joules. Then you would convert time in minutes to seconds. So 1 joule is equal to 0.239 calories. So you divide 2,000 calories by 0.239. And then you would get this amount in joules. And we're gonna, obviously, I'm gonna show you my little whiteboard and we'll work it out. Then you convert 30 minutes to seconds. So you know that 1 minute is equal to 60 seconds. So, multiply 30 minutes times 60 seconds to get the amount of seconds. Then you divide the joules by that amount of time. And that'll give you watts. So let's look at that. All right, so first we have 2,000 calories. And what I'm going to do is going to type that. Just easier. And then we have 30 minutes. And then we know all right. And so what we will do is we'll say 2,000 1,000 calories per joules, you have to multiply 1 joule over 0.239 calories. Cancel out your calories. 2,000 divided by 0.239 is approximately 8,368.20 joules. And then you have 30 minutes times 60 seconds over 1 minute is equal to 1,800 seconds. And then we know P is equal to E over T, energy over time. And that'll be 8,368.2 joules over 1,800 seconds is equal to 4.649 watts. And voila. And that's how you do that. And there's another example. It's basically working the other way, it's asking you the amount of how long must the motor operate to transfer 11,850 calories of energy. All right, and so this is an easy, pretty simple problem to do. Now, efficiency, again, I was really going to talk about the measure of efficiency. Efficiency is really just the amount, it's a measurement of efficiency that the motor is operating at. All right, so you just really just using that, you're either going to calculate the efficiency of the motor or calculate the efficiency of the motor, or you're going to determine how efficient the motor is, or you're going to determine the output of the motor based on a certain efficiency. So like this example here, not going to work. It's giving you the efficiency. It's giving you the time. And this one is actually asking you how in units of feet was the load raised. So this is actually asking you the output from not energy standpoint, but basically solving for the distance using force and work. I guess we could, since I got it up, guess we could solve it. All right, so what they're asking for, I said, how high in units of feet was the load raised? Now, it gives you the amount in kilogram. They say a 75 kilogram load was raised as high as possible in 30 seconds by a 150 watt, 75% efficient motor. Now, what we know the efficiency, we know the work, we know the power the motor produced, we know the mass of the load, right? And we know the time it took to raise this load. All right, so what will we look at? We know the efficiency equation, right? We got power in, power loss, power out. So we got power in, power out, plus power loss. And we know that important concept, efficiency is equal to the power out over the power in. So we could figure out what was the power out. We know the power in. We could determine the power lost. So let's go back over here. Problem that. All right. This is the amount of power that the motor is capable of producing. It's capable of producing 150 watts. All right. So let's go back over. Bring up my whiteboard. Clear all. Going to text. What do we know? T out is equal to T in, T lost. And we know that P is equal to 150 watts. We know the mass is equal to 75 kg. We know the time, like T, is equal to 30 seconds. And we know efficiency is 75%. All right. It's 75%. We also know that that's equal to P in. I'm sorry. That's equal to P out over P in. All right, sorry about that. My internet just went out. And of course, because it did, Blackboard is cleared. So where were we at? We were text. Let's go back. We had P in. This is P to, I think it was 100. What? Can't remember. Oh, 150 watts. Sorry. All right. And then we had math, 75 kilograms. This is me listing my knowns. I was gonna say known. What else do we know? We know T is equal to 30 seconds. We know efficiency. %. is equal to E. Oh, sorry. Yeah. Over P in. All right, what else do we know? Mass time efficiency. All right, that's what we know. We also know that E, that P is equal to E over T. We also know E is equal to Newton meter. Newton meter. So force times distance. Force times distance. Let's see. Go back up here to energy. Yeah, so energy is, which is work, is force times distance. You know that. All right. Now, if we were to draw our free body diagram. Oh yeah, I don't like that. Free body diagram. We have this mass. Go back to the problem, see what's actually going on in this problem. This is a good problem, by the way. I'm glad you asked me to do it. Yeah, example 52. All right, so we have this mass, and it's being lifted to a certain height. A certain height. Certain height H. Right, and or let's look at it this way. So if it started on the ground and it was lifted up to a certain height, H, after 30 seconds. And we just draw some type of a machine. Erase this. Some type of pulling machine. And make it like it's going, winding up. All right, so it's pulling this mass. This is a weight, right? So it's pulling this weight. Pulling that weight a certain height, and this motor has an efficiency of 75%. 75%. All right. So what do we need to do in this problem? What we need to do in this problem? So we know the efficiency, 75%. We know P N. Pn is 150 kilowatts. I mean watts. Yes, 150 watts. We don't know P out. We don't know P loss because we know P. We know Pn is equal to P out plus P loss, but we don't know P out. Let's see. P loss is the quantity wasted during the application. P out is the quantity actually applied to the task. Now, that's the question. So do we use P out, the quantity actually applied to the task, to figure out the amount of energy used to solve for how much it was displaced? Let's try it. So to solve, because we know P in, all right? We don't know P out. We need to solve for P out. We know the efficiency. So let's look at that. So if you cross multiply here, P out would be equal to 0.75 times P in. And that would give us which is equal to 112.5 watts. That's P in. And if we plug P in into this equation, we know P in, I'm sorry, we plug P out rather. P out, which was PO, is equal to E T. And then we solve for E, right? And then that would be P out, which is 5 times 30 seconds. And we know the weight because we're in kilograms. Let's see. So we multiply 112.5 times 30 seconds, you get 3375 joules. And then we know the weight, so it'll be 75 kilograms. Let me come over here. Oh, wait a minute. Times gravity, 9.8. I'm getting 735, and that'll be newtons. So if you divide so I get E is equal to, I'm sorry, 33.75. And I get W is equal to 735 newtons. All right, 735 newtons. Now, we know that energy, E, is equal to, we take force times distance, and D is in meters. So that would be, this right here would be joules, or Newton meter. So if I divide 735 newtons into 375, I get D is equal to 4.59 meters. Now you have to go back to chapter 7, I believe, to figure out length, meters to feet. So we got yards to meter. Let's see if it's in here. I found it. I'm looking in the book. Don't see it. Let's see, nope, I don't see it. So we just have to look it up. Meter to feet. So we got one. I'm gonna clear this. So we have 1 meter is equal to 3.28 feet. All right, and we got 4.59 meters, and we want to convert that to feet. So we would multiply this times 3.28 feet divided by 1 meter. Meters cancel out. And we get approximately 15 feet. So the height that the object was raised to in 30 seconds. All right, that's a good problem. Pretty good problem. Now, so what we have been waiting for, electrical concepts. Electrical concepts. So things we want to identify. We want to identify voltage, current. We'll just talk about Ohm's law a little bit. We'll discuss charge, and then we'll discuss the what do I think? I don't know. We discuss charge, we'll discuss ampere, and electrical current. Electrical current. So electrical current is a fundamental dimension or universal dimension of in engineering, right? This is another just measurement. And when you think about electrical current, the ampere is defined formally as that constant current, which, if maintained in 2 straight parallel conductors of infinite length of negligible circular cross section, and placed 1 meter apart in a vacuum would produce between those conductors a force equal to 2 times 10 to the minus 7 newtons per meter of length. All right. Yeah, I know that probably didn't make much sense to you. But when you think about an ampere, ampere is just really the unit of measure for current. That is the unit. It is an ampere, and ampere basically is the last name of some engineer, right? Last name of some engineer. So that's how we look at that. But when you think about what I just read to you, I'm going to share my screen. I'm sorry, I'm sharing my screen. I'm going to share my whiteboard. Clear this. So if you think about it, states an ampere is defined formally as that constant current which, and then we think about current. Current is just molecules passing through, flowing through, being forced through a piece of metal, right, at a certain rate. I like the way the book describes that. Yeah, I really do. Let me read it. Oh man, it kicked my, oh no, here we go. So electrical concept, and it reads, electrical charge, electrons and protons, as well as some subatomic particles, have the property known as electrical charge. On a small scale, charge can be measured in terms of the elementary charge, E. Wait, that's not it. Electrical current. And let's see, how does it specify it? It says electric current is superficially analogous to a current of water, just as a current of water is movement of water molecules in a pipe or channel. Electric current is movement of electric charge in a wire, which is sort of what I just stated to you. Electric current I is measured in amperes, named for Andre Marie Ampere. 1775 to 1836, the French physicist who is credited with discovering electromagnetism. That's not really what I wanted to read. It was something else. Where is it at? I really like the way it's stated. It is basically molecules being forced through a wire. Yeah, I can't find where I saw it. All right, well, that's fine. I can't find it. But if I find it while we're doing this, then I'll bring it back up. But what it states a constant current, molecules flowing through 2 straight parallel conductors of infinite length. 2 straight parallel conductors of infinite, right? You have current passing through 2 straight parallel conductors of infinite length that are a certain distance apart. Right, and R is your distance. That's an R. This is bad. And notice it says negligible cross-sectional area. These line wires, it's just wires, right? Of infinite length, and you have a charge or current passing through these charges or these wires of negligible length. And I'm saying distant R, but it states at 1 meter apart, which is R. In a vacuum, it would produce a force equal to 2 times 10 to the negative 7 Newton per meter of length, which would be F. 2 times 10 to the minus 7 Newton per meter of length. All right. Now, what this says that F force is directly proportionate to the distance that should be squared. Force is inversely proportional to the distance between those two wires, a constant K, and Q1, which is the charge flowing through here, charge created through this wire, times Q2. Q1 and Q2, charge created through this wire, directly proportionate to charge through wire 1, charge through wire 2, times the constant K, divided by the square of the distance between the two wires. All right. Now, if these two wires, as you do know, are flowing in the same direction, it repels. But if these two wires, the charge flowing through these wires are flowing in opposite directions, it attracts. So you create a magnetic attraction between the two metallic wires whenever you are flowing current, a charge through these wires. All right. Any questions on that? Pretty sure you have questions on that. Now, K, question KE, or K is the Coulomb's constant. And it is approximately equal to 9 times 10 to the 9 Newton meter squared per C, which is C is a Coulomb squared, and the charge is measured in Coulomb. And what is a charge? A charge is the basic law of electric charges states that unlike charges attract each other while like charges repel. Charge or flow of current and molecules through a piece of wire, you create a charge, right? Let's stop sharing. See what else we're going to get back to the. All right, now voltage. Oh, here it is. This current. Current. Am I sharing my screen? I found it. Yeah. All right. So my captions went off. I do apologize about that. But what I was saying was I found it. It's here. It's in the slides. It states that current is the change in the system, which equals how many electrons are flowing. Voltage is the force acting on the system, which is equal to the force pushing the electrons around a circuit. All right. Now that brings me to Ohm's law. Ohm's law states that V, which is the force acting on the system, which is equal to the force pushing the electrons around a circuit, or voltage. I is the change in the system, or how many electrons are flowing, or current. R is the internal resistance in the system, resistance to the flow of electrons, which I know you could have read that, but that's pretty much Ohm's law. Now, I did skip a slide. Power is equal to work over time, work times distance, but power is also equal to electrical work over time. Electrical work is equal to voltage charge. Voltage charge. So P is equal to VI. So power is voltage charge divided by, electrical work is equal to VI, and then power is equal to VI over T. All right. And power, voltage, charge, time, power, voltage times current, right? Which is VI. Oh, no, so I said it wrong. Power is equal to VI. Electrical work is V. What was C? Can't remember what charge is. Charge is Q, which is so BQ. Sorry, I said that wrong, Cross. So electrical work is BQ. I'm pretty sure you all saw that before I did. All right. Anywho, so I stubbed my toe again. Let's look at an example. So we got the computer system on the Indian Mars orbiter mission requires a 5-volt power supply cable of delivering a peak power of 205 watts. And it asks, what is the resistance of the computer in units of ohms? So what do we know? We know we have power, we have voltage, and they're looking for resistance. What do we know what resistance is? Well, we just stated what resistance is. Resistance is equal to V, is equal to, V is equal to current times R, which is the resistance. So R is equal to voltage divided by current. Voltage divided by current. They gave us the voltage. They didn't give us the current, but they gave us the power. And we know that power is equal to VI. So we have the current. We have the voltage. Now we can solve for resistance. So this is pretty straightforward stuff. Using Ohm's law, clear that out. We know that V is equal to IR. We know that P is equal to VI. Right? So we know that we substitute in for I. I is equal to P over V. Sub that in for I. Then you got V is equal to P over B R. So we know R is equal to, if you cross multiply, flip the second and cross multiply, right? You're gonna have V squared over P. And so we have V squared, which is 5 volts, squared over 205 watts. And that comes out to be 25 divided by 205. And it is, R is approximately 0.1219. And you just round that up to 1 decimal place, so it'll be 0.122. And that's all we have for chapter 8. If you have any questions, feel free to email me. Thank you for listening.